This starts off Unit 4 with Chapter 11. First thing we'll talk about is simple harmonic motion, and particularly in this video we'll look at just sample and practice problems A. First thing I want to introduce you to is the mass spring system. If you look at Figure 1 on page 368 in your Holt textbook, you'll see a really good picture that I can use to display positions A, B, and C off of that diagram. When you first look at this, you're going to see that you are pulled at a maximum displacement. So here, I have an example of what we would see with the mass spring system. Now with this mass spring system, this is at equilibrium right here, okay? It's at rest, it's at equilibrium. It's not going to expand any further, it's not going to contract any further, nothing like that. So no compressions or anything will be seen. So if you pull down on this an additional like 5 meters or whatever, that would be called the maximum displacement because it's the maximum displacement from equilibrium position. Once again, your equilibrium position is this current position right here because it is at rest. It is not going to be stretched any further. It's not going to be compressed any further. And then finally, maximum displacement, these say the same thing, but they're going to mean something opposite. Once again, this first one is like, okay, I pulled down 5 meters. So you can imagine this thing is going to then oscillate back and forth. It's going to vibrate up and down and up and down and up and down and up and down. Okay, like a slinky, just hold a slinky there. It's going to vibrate up and down and up and down. So that's what we're looking at here. So your first maximum displacement, your second maximum displacement, your first maximum displacement, your second maximum displacement. Okay, so that's what we'll look at with this system. Once again, you can see that picture drawn out for you on page 368. A couple of things I'd like you to add here with this, guys, is maximum displacement F and X are opposites. In other words, you're going to have a positive F and a negative X, or vice versa, okay? Equilibrium position, your F will be equal to your X because you have no displacement. Your displacement is equal to 0. Therefore, your F is equal to 0 newtons meters. We'll see an equation evolve from this here very shortly. And then for maximum displacement, once again, F and X are opposites. But when we say that now, like how the first one was a positive F, now we're going to say a negative F and a positive X. Guys, please understand that these can switch. It's not always that the first maximum displacement, A, maximum displacement is going to be a positive F and a negative X. No, it just depends. If you pull down on something, right, then you increased its displacement. Whereas if you compress something, then you decrease its displacement. Just remember that F and X will have opposite values. Signs, in other words. Okay, so number 2, process would continue indefinitely. So think about like the Newton balls that used to be on my desk, the Newton's cradle. With that, it would continue back and forth, oscillating like a simple pendulum forever and a day if it wasn't for the presence of what, guys? Stop and think about this. What is present that makes this system stop? Well, that process that would continue indefinitely would be a true statement if it were not for the presence of friction. Friction is then going to convert some of that mechanical energy, kinetic to potential, potential to kinetic, kinetic to potential, potential to kinetic. Okay, it's going to convert some of that energy into non-mechanical energy in the form of heat, light, and sound, just like on the Newton's cradle there. What we refer to that as is damping. Okay, you do not call it friction. Now that we're talking about simple harmonic motion, you refer to it as damping. Moving right along. The definition of simple harmonic motion, it's a big one, so take your time on this, please. Definition, vibration about equilibrium position. Vibration about the equilibrium position. In which a restoring force, trying to restore it back to that equilibrium position because everything is happy at equilibrium, is proportional to think about this. Vibration about equilibrium position, so you're oscillating past the equilibrium, back towards the equilibrium, past the equilibrium, back towards the equilibrium. Okay, so vibration about equilibrium position in which a restoring force is proportional to the what? What did we talk about on this slide? Okay, what would your force be proportional to? It'd be proportional to the displacement from equilibrium. Displacement from equilibrium. Simpler definition, we're going to start using some physics words now, is oscillation over repeated path. Oops. So layman terms of that is back and forth motion. So like swinging on a swing set, teeter-tottering on a teeter-totter. Okay, that's back and forth motion. So that's simple harmonic motion. Number 1 here, in simple harmonic motion, displacement is proportional to, check out your definition there. What is it proportional to, guys? It is proportional to restoring force. Your definition of your restoring force is when mass is pushed or pulled towards the equilibrium position. When mass is pushed or pulled towards the equilibrium position. So you can see over here that you started at your equilibrium position and then you went down some. So you pulled down. That means then that's your displacement, that your restoring force is going to want to push up, right? Because it wants to get back to this equilibrium position. Okay, so that's what the restoring force is. It's going to work opposite, think about that first slide, the displacement. So the equation that we're going to assess here, in this equation you need to know, is F elastic equals negative quantity Kx. I kind of don't have too much room here, but your F elastic will be in newtons. Your K is your spring constant, and your spring constant is newtons per meter, and your displacement is obviously meters. Okay, so it depends on what variable you would be solving for. For your practice problems, a lot of them are going to be your spring constant, so newtons per meter is what you would want to look at. Okay, next here we have elastic potential energy. Elastic potential energy is also going to be known as EPE. It is present in a stretched or compressed spring, string, bungee cord, etc. I'm just using the word spring there. The equation that you're going to want to use, this should be a recap. EPE equals 1/2 kx squared. I don't think we need to go over that again, but you do have joules, you do have newtons per meter, you do have meters squared. Okay, bow and arrow system. So think about pulling back on a bow, and you have an arrow attached to it. So with that, when you pull back on the bow, you are storing EPE, elastic potential energy. When you release the bow string, then that EPE is converted into KE, energy of motion, right? So stop and think about this. If all mechanical energy, conservation of energy, then what is not present? So if all energy, all EPE is converted to KE, all KE is converted to PE, then you have no friction that is present in the system. Make sense? There'd be no friction. And if there was no friction, then that would mean that there would be no heat, light, or sound dissipated from that system. Okay, next thing we have is gravitational potential energy, also known as GPE. The two constants that we're going to have here, well, that requires you to remember the equation. The equation for GPE is mgh. Yes, mgh. Well, the two things that we're going to keep constant here usually are your mass. You're not losing mass as you're falling or moving or swinging on a swing or whatever. So mass is going to be a constant, as well as free fall acceleration. Please don't call it gravity. It is not gravity. Gravity is measured in newtons. Free fall acceleration is measured in meters per second squared. GPE and H then are going to be directly related from your equation of GPE equals mgh. That makes sense, right? Because m and g are your constants. GPE and H are directly related to each other. So think about this. GPE is greatest at what position along a pendulum's path? Well, think about this path right here. So you start right here, and you push back, and then, yay, you're swinging. And you go back to your start position, and you're swinging back here. And you go back to your start position, okay? Where are you going to be traveling with the most GPE? GPE is going to be greatest when your velocity equals 0 meters per second, and your height is greatest. Oops. Doesn't that make sense, guys? When your height is your greatest is when your GPE is going to be the greatest, because H and GPE are directly related to each other, okay? So therefore, the height of the path, the furthest position from equilibrium. Sorry about that. So here, okay, on a swing then, the highest point of the swing will be your maximum displacement. Your KE is going to be 0 joules, right, because you're not moving. Your GPE is going to be at its maximum position, or its maximum value, maximum joules. At the lowest position of the swing, now you're at equilibrium, okay? So this part is talking about this part is talking about this. Okay, so at the lowest point of the swing, what we're looking at is a KE of max, because you're traveling the fastest, okay, because this is where you're going to have your greatest velocity, and your GPE is going to be 0 joules, or at least it should be if all of the PE is converted into KE. Heading towards the equilibrium position, so this one is looking at like in between the positions there. You're going to be gaining kinetic energy and losing potential energy. Something that I would like you to mark is look at table number 1 on page 375. This will definitely help out with this concept that is right here. Okay, sample problem A. You have a mass of 0.55 grams. You have a displacement of negative 2.0 centimeters, but you know that you really want meters, agreed? So that should be negative 0.020 meters. Your G is 9.81 meters per second squared, and you're solving for your spring constant in newtons per meter. So from this equation, from this problem, you know that the equation that you want to use is Hooke's law. F elastic equals negative quantity Kx. You want to solve for K. So F over X equals K. Your F elastic is not known, so that's really going to break into mg over x is going to be negative k. So that gives you 0.55 times negative 9.81. It's falling down. And your displacement of negative 0.020 is going to give you 270. So your final answer is 2.7 times 10 to the second newtons per meter is your spring constant. Okay, so now you want to try your practice problems, which I will give you marked in our problems on my teacher page.